Okay, so you've just turned in homework number 2, and the third assignment is available now on Blackboard. And the third assignment is confined exclusively to what we're covering in today's class meeting. It's three reservoirs. We may also talk about three reservoirs problems in class on Friday, but the point is you'll have plenty of time to solve this assignment because the only thing that's on homework 3 is three reservoirs problems, and you're going to know how to solve them after today. Okay, well, let's just go ahead and dive right in. Let me give you the setup here in this classic three reservoirs type problem. In the three reservoirs problem, what we have are three different reservoirs that are connected together at a central junction. And so you can see that in this sketch what we have is one reservoir that's at the highest elevation. In this case it's labeled as reservoir B, and then another reservoir at the lowest location which is labeled here as reservoir C, and then there's one somewhere in the middle. And what we're talking about isn't so much their physical location as the water surface. And so the same thing would apply even if the tank A was really, really deep, and if tank A was deeper than tank C, it wouldn't matter. It wouldn't change a single thing. It's just the water surface elevations that are the thing that determines which is the high, which is the low, and which is the medium. And so in that same regard, these three reservoirs could be on flat ground, and they could be the same size, but it's just that there's different liquid levels in each. That would also be a three reservoir problem. The three reservoir problem is simply defined as three reservoirs connected together at a central junction, and there's three different water surface elevations. All right, so they come together here, and that junction is labeled as D. Now, by inspection, we know which direction the water is going to flow for two of those reservoirs. We know, for instance, that the flow is going to go from reservoir B towards the central junction. And so here you can see that an arrow indicates that QBC is going from tank B towards the central junction. So it's the water's flowing downhill. Newsflash, right? And then the same thing is true at this lowest reservoir. It's obvious. We can tell just by looking that the flow is going into the tank, from the central junction into the tank. But what we're not so sure about is what's going on through pipe AD. And so, it could be one of two things. It could be that the water is flowing from the upper reservoir B, and it's flowing into both A and C, and so the water could be going down and then flowing to C, and then it could also flow over here to A. So that's one possibility. Or it's also possible that the water from this middle reservoir A is feeding into the lowest reservoir C. And so we have to go through some calculations to find out what direction the flow is for the middle reservoir. And because of that uncertainty, we also don't know right at the outset what are the flow rates through all three of these pipes. And so what I'm going to be introducing you today is a calculation process that will use Microsoft Excel to tell us what's the flow rate through each of these conduits, and then whether the flow is going in or out of the middle reservoir. Okay, so does everybody understand the setup so far? The central uncertainty, the question that we've got here, what we're trying to solve is how much water is going through each pipe and whether it's in or out of the middle reservoir. Okay, so that's the problem. We don't know which way the water's flowing. We don't know how much is going through each pipe. And then this third thing that we're going to be interested to try and solve is what's the pressure at the junction. And that can be important for a variety of reasons. We may have a pipe strength that we need to check and make sure, maybe for instance, that our welds are going to hold under whatever pressure is there. But also because when we know the pressure at junction D, then that helps us to establish the head loss through each pipe. So that's kind of part of determining what's the flow through each pipe, is determining the amount of energy at this central junction, the head. All right, so let's start with what we know. On the left side is the problem. What are our tools for solving the problem? Well, one thing that we know is that water flows downhill out of the highest reservoir, downhill into the lowest reservoir, and the reason why is it flows away from where there's the most energy and towards the location where there's the least energy. And inside the reservoir, the energy only exists as elevation. Remember that the three places the water can have energy is as pressure head, elevation head, and velocity head. And so inside of a tank that's open to the atmosphere, there's no pressure head, there's no velocity head, but there is elevation head. And so it goes from high energy to low energy. But in the middle reservoir, the reason why we don't know whether the water is going to flow in or out is because we have to understand more about the head loss through this pipe before we can determine whether the pressure at D will be driving the flow into A, or whether there's more energy at A than there is at D. So now that we're thinking in terms of energy, that's what dictates the direction of flow through pipe AD. The water goes from A towards D if there's less energy at D than there is at A. But if you've got a really high pressure at D, and depending on its elevation head as well, you look at the total amount of energy at D, and if there's more head at D than there is at A, then the flow will go from D towards A. So the flow rate depends on the difference in energy through each end of the pipe. So we're going to use that as a general rule that if the head is higher at one end, then the water flows from that end towards the other. The methods that we've learned so far for determining head loss can still apply here. We could use the Darcy-Weisbach equation. We can also use the Hazen-Williams equation. So we can calculate the head loss through each pipe. And so here's our formula for do it if we're using Darcy-Weisbach. But the problem with this formula is that at the beginning we don't know the flow velocity. And we also are already acutely aware of the fact that our friction factor F depends on the flow conditions. And so there's really two things we don't know. We don't know F and we don't know V. And F depends on V. So boy, that kind of compounds the things that we don't know. Our method so far this semester has been to start with a guess, and we're going to do that same thing today. And another kind of governing equation that we have that tells us if we're on the right track is we can apply continuity at junction D. You maybe remember this word continuity from chapter 5 last semester in fluid mechanics. Continuity equation is Q equals VA, and that in a control volume, flow in equals flow out. And so here at this junction D, you can't have more water flowing into the junction than flows out of the junction if there's no capacity for storage. And junction D is not a storage tank, it's just a spot where three pipes are coming together, and it's full of water, and so a certain amount of water that comes into the junction has to be going out. So we're going to be doing a continuity check to see if our guess of the flow rates honors this requirement that flow in equals flow out at the junction. So that's going to be a part of our spreadsheet process. Now, just a quick word. I think this is the third spreadsheet template that I'm giving you. This course is not about taking a template I've given you and just putting numbers into it. It really is important for you to know the underlying method. And in past semesters, I didn't give students a template to begin with. They had to construct the spreadsheet solution from their very own. But what I found over time was we could cover more ground and get into more detail if I give you the bare bones and then you fill in those bones with your own formulas and inputting the data. But I just wanted to give you a warning that just because you can take a template file I'm giving you and find the right answer doesn't necessarily mean that you understand the underlying content. And so it's important that you read the book and you really sincerely think about, like, what is this method doing and why is it set up a certain way? I don't want to take too much of the thinking out of the process for you, but I think maybe the templates can be okay if you're warned that you still need to be thinking about why things are set up the way that they are. So our method on an iterative basis are going to be, we're using these governing equations. All right, so our definition of head is, that's just another word for energy, but it's measured with units of length. And so because pressure is divided by gamma, that means that the pressure head would have, in SI units, meters, in traditional units, feet. Elevation likewise has units of length. Velocity head, when it's v squared divided by 2g, you'll end up with units of length. Okay, so we can find out the head at D, and we can also know the head in each of the tanks. It's just going to be the elevation of the water surface. And of course, this is our formula for determining how much energy loss there is through the pipe. Now, how much head is there at D? You'll notice that I've got a plus for one of these formulas and a minus for the other. Let me explain why. The head at D, in terms of tank A, we already know that the water's flowing out of tank A because it's the one with the highest water surface elevation. So it's known that the water goes from A towards D. That flow direction is given. So therefore, that must mean that there's less head at D than there is at A. Let me put it another way. The water wouldn't flow from A to D if D had more energy. So D has less energy than A does. And so therefore, the head at D is however much head there is at A minus the losses through that pipe AD. I hope that makes sense. And in a similar regard, here the junction D has a certain amount of head that is the head at C plus. And so now it's the plus because we're going against the flow direction. The water is going to go from D towards C. So what that means is there must be more head at D. And so the amount of head at D is however much there is at C plus the losses through the pipe. So that's why it's plus when we're going to D from C, is because we're going against the flow, meaning we know that the head at D is greater than C, so we're adding. But we also know that the head at D is less than the amount of head at A, so we're subtracting. Now I've just given a guess flow rate. Let's say, what if the flow is going, just as a guess, from B to D? Then we could also write a relationship at the head at D relative to the head at B. So we'll guess some head at D, and sometimes a decent starting point for that guess is just to assume it has the same amount of head as the water surface elevation in the middle reservoir. That's a fine starting place as any other. Then we're going to use these equations for head loss in terms of F and V. So we'll use the Darcy-Weisbach equation or Hazen-Williams as appropriate. And in our first part, we have to start with an assumed value of F, or if we're already going through this iterative cycle, we use the most recently calculated value from the previous iteration. And then when we know F and we know the head loss, we can solve for V. Then we're going to determine what would be the Reynolds number for that newly updated value of the velocity, recalculate a corrected F value, an improved guess of the velocity, and then from that improved guess of the velocity, determine the flow rate, and finally check to make sure that in equals out. And it won't at first, but whether or not there's more flow going in or more flow going out tells us how we should change our initial guess. And the criteria is that if the flow out of the junction is larger than the flow in, then that means that your guess of the head at D was too high and you need to lower it. So think about why that would be. If you have a lot of flow out but not as much flow in, then that's assuming that D has lots of energy. And so there's not much flow going into D because it's a high energy location, but lots of flow out. So if this, then in your next iteration you'd lower the guess, but if the out is greater than the in, it's the opposite. In your next iteration you'd raise the guess. So we can combine this iteration with also a little bit of goal seek, but you can't goal seek too early. If you try and goal seek right in the first iteration, you won't get an accurate solution because we want this to converge according to two criteria. We want it to converge according to the F values are no longer changing from iteration to iteration, and also flow in equals flow out. And so this is a two criteria iteration, and both must be satisfied for us to have an accurate answer. Any questions about the method? You know you're done when flow in equals flow out and when the F values are no longer changing. All right, so here's the example. We're going to use these specific values that are shown on the screen. This is a traditional units problem, and if you have the template file that I gave you, please open it now. I hope that you're able to work on one screen while you watch on another. And so if you can bring up the lecture on a tablet or a secondary computer, or maybe you've got your laptop plugged into the TV and you can watch this on the TV while you do your calculations on the main screen. We're going to follow this process that I've just outlined for these values, which are also translated into our template file. So that same drawing is there on the template file. We've got our elevations. Reservoir B has a water surface elevation of 120 feet. Reservoir C has an elevation of 70. And then A is in the middle. The flow is kind of indeterminate there. That's the one where we don't know if the flow is in or flow is out. So any questions before we start chugging through this solution together? Now if you do have a question as we're going through, please stop me. This only works if you understand the method. And so don't feel ashamed or bashful if you need me to clarify a certain thing, or if I get carried away and I'm going too quickly. Slow me down, reel me in, let me know that you need to see the formula for another thing. We've got plenty of time. We've got 30 minutes until class is over. So it's better that we all understand this. That's more important than getting through both of the examples in today's class. Okay. So the material of each pipe is given. We could go to a table and look up the equivalent sand roughness. So cast iron, for example, we looked that up, 0.00085. And we've got that same cast iron for pipe BD, but DC is galvanized. And galvanized pipe is a little bit smoother. It's 0.00050. Okay? And you can tell from the sketch the given length of each pipe, AD is 750 feet. 750. BD, you can see here, it says 1,000 feet. And DC is 500 feet. All right, zooming in a little more. That's good. Okay, diameters are given. So AD has a diameter of 8 inches, and we want the diameter to be in feet. So I'm going to write 8 divided by 12 to get the diameter in feet. And likewise, we'll do that same conversion for pipe BD. So that's a 12-inch pipe, which is 1 foot diameter, and DC is 8 inches again. So equals 8 divided by 12. Okay, so far so good. Raise your hand or ask a question, interject somehow if there's anything I can clarify. Okay, so the cross-sectional area, pi d squared divided by 4. Pi times d squared divided by 4. Okay, so that's the diameter. And I can just drag that down through all 3 of the pipes. Now, what should we do for our first guess of how much head there is at D? Let's guess, what if it was, I'm gonna break the cardinal rule of examples. The cardinal rule of doing an example in class is never do anything that you don't already have written down in front of you. But I think it'll be a little bit easier to understand if we guess that the head at D, no, I'm not going to break the rule. All right, let's guess that it's 110 feet. What I said earlier was that you can, as a middle guess, just as a starting guess of the head at D, assume it's the same as the water surface elevation at A. So 110 feet is going to be our, all right, Jeremy convinced me. I'm going to be a rebel. 111 feet. All right, we're going to guess that there's 111 feet of head at D. Okay, so I'm just going to refer to that same initial guess for all 3 of my guess head values. And so then what does that mean about the head loss through the pipe? So we're going to have to be smart about this, me especially, because I'm now walking without a net underneath this tightrope. Okay, so the head loss through the pipe. So if there's 120 feet of head at B and 111 feet of head at D, so the head loss is our elevation of 120 minus this guess value. So that tells me that by definition there's 9 feet of head loss through that pipe. I was looking at the wrong, I was looking at B. I apologize. I'm already regretting it. No, elevation of A is 110. Okay, so if there's 110 feet of head at A, then the head loss is the guess value minus 110. There's 1 foot of head loss. All right. Now through BD, it's going to be 120 minus this guess. So there's 9 feet of head. I mean, that makes sense, right? If we know the amount of energy there is at D is 111, then it's 120 minus 111. And so we know that there's 111 feet of energy at D, so then that means that the loss through the pipe to get from D down to C is going to be 111 minus, oh, I guess I don't need to type 111, 111 minus the elevation. Okay, so hopefully you've got these values on the basis of a reference to this guess. And the reason why we want a reference to that guess is because we're going to copy and paste in subsequent iterations. And so we want to have the actual water surface elevation for each of the reservoirs kind of hard-coded into that formula. Okay, so our guess F value. Let's just start off by guessing a middle F value of 0.02. And we'll do that for all 3 pipes. Okay, so if we have an F value of 0.02, and if we've got these diameters and these lengths, then what is the velocity? So you'll notice here in this formula, I've rearranged the Darcy-Weisbach equation to solve for what is the velocity when you know the head loss, when you know the diameter, when you know the F value, when you know the length, you know the gravitational constant G is 32.2 feet per second squared. So let's solve for V. Okay, so it's square root SQRT of h sub f times the diameter of the pipe times 2g, so 2 times 32.2. And then in the denominator of that square root is our f value. It's our guess. Now, I've got this equation centered, and so now the equation is on top of where I would click to get the f value. So I can't click on that location to get the f value because like the equation itself is on top of it, but I could type in I-27 and get the same result. I couldn't click there, but I could type the cell reference. All right, so dividing by f, we just did the f part down there in the denominator. Now I need to multiply by the pipe length L, close parentheses, and close parentheses again. Okay, so you've got that, type enter, and we have a guess f value of 1.69 feet per second. So that would be the velocity through the pipe. And I can just click and drag, let's see, yeah, I can just click and drag down and get the corresponding velocity for the other locations as well. Okay, now do you remember the Reynolds number equation? Do I have the kinematic viscosity of water on here anyplace? I don't. I think it's 1.1 times 10 to the minus fifth. Let's see, I know that we had that in the example from other day. Here it is. Yeah, we're going to need this kinematic viscosity. So let me copy that over here, because we're going to use it to find the Reynolds number. We're in traditional units. Okay, so Reynolds number, V times D divided by kinematic viscosity. So the velocity times the diameter of the pipe divided by kinematic viscosity. So 1.22 E minus 5. Okay, so I've got a Reynolds number now for all three of these pipes. Now, I can, rather than just having our guess F value, I'm going to use the Jane equation to estimate an updated F value. So I've got the K sub S and the D, I've got a Reynolds number, so I can consider both terms in the denominator and have an updated guess value of F. So I'm going to be using the Jane equation. 1.325 divided by, parentheses, natural log. Okay, so the K sub S is here, divided by 3.7 divided by D. I don't have to use the parentheses necessarily. I could just do the double divided by, and it's going to give me the right result. Plus 5.74 divided by the Reynolds number. Now I can't click on the Reynolds number because my equation's in the way, so I'll just type K27. And that references where the value is for the Reynolds number. And the Reynolds number needs to be to the power of 0.9. And then all of that is squared. Okay, so are you with me? Are there any questions? We've set up the Jane equation, and we're going to have an improved guess of the F value for all three of these pipes. Okay. Now, we can do this one again. We can find the updated guess of the velocity because we have a better guess of the F value. Okay, so the velocity is square root of h sub f times d times 2 times g divided by our newly updated guess of the F value, which is in cell L27. I guess I should not center these formulas. Looks pretty in the end, but it gets in the way as we're typing. Divided by the length. Okay. So it did change that velocity a little bit because we have a now updated, better guess of the F value, what it might be. I can apply that downward through the other two pipes. Okay, now flow direction. Is the flow going into the junction or out of the junction? Okay, so in AD, we said that it's 110 feet of head in the tank, and there's 111 at the junction. And so the water is going to go from the junction to the tank. And so I'm going to call that flow direction to the junction is out. Yeah, it's going out from the junction towards the other tank, whereas it's into the junction for pipe BD and out from the junction towards the tank for DC. Just think about if you've got 111 at D, the water is going to go to D from this upper reservoir B. It's going to go from D to the tank for both reservoirs A and C because there's more energy at D than there is at either of those reservoirs, and so the water is going to go out from the junction towards the reservoirs. All right, flow rate. Q equals VA. V times A. Okay, so we have a flow rate through each of the three pipes. Now, down here at the bottom, we need to combine the flow rates. And so we're going to do the out minus the in. So it is this one and that one minus the in. Okay, so we have more flow going out than going in. You can kind of just look at it. 4.7 plus 0.5. So there's more water going out of the junction than is coming into the junction. So then what does that say to our rules if in is greater than out? Let's go back to these rules that we had set up earlier. If out is greater than in, then lower the guess for HD. And that's the situation that we face. Out is greater than in. If out is greater than in, then guess of HD is too high. Okay. So conclusion, our guess for HD was too high. We will lower it. Let's try 109. Now we have to be careful though, because when we try 109, that's going to change the flow direction from A towards D. So before, in our earlier guess, the water was going from the junction towards this middle tank. If it's 109, then that's going to adjust the flow direction. So we're going to have to we'll be able to copy and paste most of what we've done already, but we're going to have to make some manual updates along the way. All right, so let's get into that. I'm going to copy all of this. You can do the same. Control C, and then click down here, and we're going to paste with Control V, and it repeats everything exactly, but we can do some updates. So the first update is we've got a new guess head value, right? So our new guess, we said we're going to do 109. So that changes all of those. Now, this is no good. We have to change our guess of the head loss because the water is going to go from A towards D. So there's no such thing as a negative head loss. So we're going to have to say that the head loss is 110 minus this guess value. Now that's right. Okay. Now what about through pipe BD? So we're going from 120 down to 109, so the head loss is 11. Okay, that's fine. And if we're going from 109 down to 70, that means we're going to have 39 feet of head loss through pipe DC, so that's good. Okay, so we've made our update to the guess of the F value. Now, we wouldn't start over with another just guess of 0.02. Let's use the most recent values. Let's use these from before, because those are more accurate. So I'm going to reference that location that has the F value from the previous iteration for the pipe in question. Let's click and drag that down. Now, the formula is still valid. We don't have to type that in again. The formula for Reynolds number is still good. We don't need to type that another time. This updated F value is in good shape. This velocity is still fine. Now we do need to double check these flow direction assumptions though. So I'm going to delete that all out. Okay, so the water from A to D. Okay, if the elevation of the water surface is 110, and we've only got 109 feet of head at D, then what happens is that the water is going into the junction. Last time it was out, but now there's less energy at D than there is at A. And so it's going to be in for this pipe, and it's still in for this one, and out for that. And it's really critical that you understand how to label whether it's an in or an out. You just look at what's your guess for how much head there is at D, and then you compare it to the known water surface elevation for each of the three reservoirs. Okay, our flow rate is velocity times area. The interesting thing is that these flow rates aren't that much different, but the question is, are we getting closer to balance than we were before? Let's delete out that previous formula that we had for the flow balance, and we're going to do the outs minus the ins. So equals the out, okay, minus both of the ins. It's negative. So what that means is that, let me delete the previous conclusion that we had from last time. Our criteria is that if the out is less than the in, then raise the guess. So in is too big. That means we need to raise our guess. So this is like Goldilocks, right? The porridge is too hot, the porridge is too cold. So 111 is too big, 109 is too small. So our next iteration needs to be, let's try 109.5. So I'm going to copy everything. Oh, I didn't type my conclusion. Our guess for HD was too low. We will raise it. Try 109.5. That's too far zoomed in. Okay. So copy and paste. Control C, Control V, and we're going to have a new guess, 109.5. Okay. So if we've got 109.5 feet of head at D, there's just going to be a little bit of head loss through that pipe that connects the middle reservoir and the junction. All this other stuff is still valid. We haven't crossed the threshold, the 110 threshold that would have swapped the flow direction again. We've got less error here. So we can kind of just iterate a little bit now, right? Like, we want this error to be as small as possible. So what if we say 109.6? Oh, it's even closer. 109.7. Getting better. But that's only one of the criteria. Remember that we also need to make sure that our F values are stabilizing. So 0.023, 0.025. So we won't be able to get all the way there necessarily just with this part. But let's do a goal seek. Our goal seek is we want this to be 0 by changing our guess of HD. So data, what if analysis, goal seek. My goal, set that to 0 by changing the elevation. Go for it. Oh, all right. It was looking hairy for a second there. The F values aren't stabilized, but this gets us a pretty good guess to use in our final iteration. So let's do this whole thing again. Copy. Oh, by the way, how's our out and in is equal, but we just don't have convergence with the F values yet. So that's why we are going to copy and paste one final time. And in doing that, now the F values are stabilizing a little bit more, where, you know, like what's an okay threshold? Like if it's within 2% or so, let's check the percent change of the F values. So this minus that, let me put parentheses around it, divided by the new one, and times 100. So that's only 1% change. The rest of them is even less. So we're golden. We've converged. So our conclusion is there is 109.88 feet of head at junction D, and the flow rates are as indicated here. So these are the flow rates that will go through the pipe. So we've solved it. We've cracked the code. Now we've just got 7 minutes to do the second part of this example. And the second part of this example is did I have the kinematic viscosity all along? Not on the spreadsheet anyway. Find the pressure at junction D. Okay, we know how much head there is at junction D. So the physical elevation of junction D is it's at 85 feet. And so the head at D is what we've just calculated. Here's our previously calculated head at D. The elevation is 85 feet. That's its physical location, you know, maybe above sea level or something. And then what we're going to do is subtract out the average velocity head. And this is probably being pretty esoteric here, where we're even bothering to consider the velocity head. We could just calculate the pressure based on the elevation, but we'll be sticklers here and use this velocity head. So velocity head through pipe AD is going to be V squared divided by 2G. So that's how much velocity head. Is that really 0? Very little velocity head there, right? Oh, there's not much flow going through that pipe. And then I can drag that down for the others. And then the average velocity, I guess the velocity is pretty high through pipe DC. So the average velocity head, and then what we're going to say is that the pressure there, if we solve the energy equation, this is what we define as head. So if we want to find the pressure at one location, it's going to be the head minus z minus velocity head multiplied by gamma. Okay, so it is the total head minus the elevation minus the velocity head, and then we need to multiply all of that by our unit weight of water, which is 62.4 pounds of force per cubic foot. Oh, what did I do wrong? Oh, I didn't have the multiply sign, but it knew what to do. Yes, that's right. So that's our pressure in feet per square foot, and then PSI, there's that many feet in a square foot, there's going to be less in a square inch because there's 12 inches by 12 inches in a square foot. So we have to multiply this answer by 144 to find out the pressure in PSI. 10.3 PSI. Jeremy, I'm glad you encouraged me to be a rebel. And I had an early misstep at the beginning, but that was a much more interesting example than if we had used that milquetoast initial head elevation of 110. Are there any questions? Certainly there must be questions. Is anyone still awake? No. Okay, thank you, Jeremy. Your praise is all I really wanted. And now I've got it. No, what I really want is for you to understand the three reservoirs problem. But what I want in addition to that is I want you to just say, wow, that's just so exciting. I want you to know how to do it, and I want you to be excited about it. I want you to love the three reservoirs examples as much as I do. It's like when you post pictures of your kids on social media. You want people to like those pictures, right? I don't post pictures of my kids on social media, but I maybe post spreadsheets on social media. I do, in fact. I do. All right, well, that's all the time we have for today. So when we get together on Friday, is there any reason to be worried about this? No. That's close enough, the in minus the out. We could do another what if. We could do one more goal seek. That's a great question, by the way. But it's close enough that I don't think it's going to change our head if we do adjust it a bit further. You know, goal seek, you're not able to control the convergence criteria, but you can for what if analysis. Later in the semester, we're going to need to use what if analysis. No. Solver. We're going to use solver instead of goal seek later on because then we can get it even closer. Here it doesn't matter. Great question though, I'm glad you asked. Do I want you to make different tabs for the homework? Yeah, I think you should. You know, your homework assignment, I ask you to solve a couple of different three reservoirs problems, and it's better if you put each of the questions on a different tab. So when we get together on Friday, we're going to do a Hayes and Williams three reservoirs. So it'll be a nice practice. The method will be largely the same, but a little bit easier because the F value that was constantly changing on us in Darcy-Weisbach, we cut through some of the layers of uncertainty. But you know, if you can climb this mountain, you can certainly climb the Hayes and Williams mountain. Well, all right. That's it for today, everybody. Remember that your next homework is due on Wednesday of next week, but you could already get a real early start on that if you want to start playing around with three reservoirs. That's all I have for you today. Thank you for your participation. I'll see you Friday.